Hello, everyone. It is the top of the hour, and it is time to begin another one of Atlas's online Weathering Academy seminars or webinars. Today's presentation is part 2 of our series of fundamentals of weathering presentations on natural or outdoor weathering. My name is Matt McGreer, and I will be your host for today. The standard, kind of format applies. This event will be approximately 1 hour. Everybody is on mute, and there is we'll talk about questions. I've got a slide on that in just a little bit on how you can ask some of your questions. So we will get to that and go ahead and get started. A little bit about myself. You see, I've been working in weathering testing now for a little over 30 years. Started my career actually working at one of our outdoor weathering sites, just as a weathering technician, eventually became the evaluations manager at the Weathering Services Group facility in Phoenix, Arizona. At that point, right around the turn of the century, I moved to our headquarters here near Chicago, Illinois, where I became the client education manager for events such as this. Then took a little bit of a turn in my career and was a quality director for a few years, and then spent much of the last several years as product manager for our weathering instruments, and that includes the standards management at that time. And just earlier this year, I was offered the position to be the director of the Atlas Weathering Services Group, so it's probably appropriate that I would be giving this presentation since the testing that we're going to talk about today is kind of all under my purview now. You see my educational background there, and probably the most important thing about this slide is noting that my email address is matt.mcgreer@amatech.com. And so I note that because even though we're going to talk about how you can ask questions with a little housekeeping slide that we have here, if anybody has any questions after we complete the event for today, you can always feel free to email me at matt.mcgreer@amatech.com, and I'll be happy to get back to you. So as I noted, everybody is going to be muted today. Just a lot of people that are on the line and on this webinar, so we'll do it that way. But you will notice that on your GoToWebinar dashboard, there is a little questions tab. If you open that up, you can type in a question, and when we complete the actual presentation for today, we'll try to answer as many of them as we can. Note there that the presentations will be distributed after this seminar is complete to company email addresses, and then we'll also ask, if you can, please fill out a short feedback survey after this event. As mentioned, this is part 2 of the Fundamentals of Weathering series. Hopefully many of you were listening in on Factors of Weathering. This kind of takes the information about climate and then applies it then to the actual application of weathering testing. And there you see the other series of events that we have in our Fundamentals of Weathering. And we'll talk about how to sign up for those if you haven't already at the conclusion of this event. We always start off our presentation with a simple little slide on who Atlas is. We have over 100 years of weathering testing work and innovation. You see here at the top left our accelerated weathering instruments using different types of light sources. There are xenon light sources, fluorescent UV, metal halide. Here you see a corrosion cabinet in the middle here as well. What we're going to be talking about today is the outdoor weathering testing, such as the picture that you see right here and some of these things. Also, as a part of the weathering services, we also do laboratory weathering services as well, with 2 primary locations, one here in Chicago, one in Germany. On the bottom left, we see the Atlas Custom Systems. These are typically using either an LED or metal halide light source to test, I like to say, planes, trains, and automobiles, because we actually have a train car in a climate chamber freezing right there with these this bank of lights that you see here, or an actual full-size airplane under a series of luminaries here. These types of custom systems are also sometimes used for high-speed crash testing. They have a very stable power supply, stable lighting system, so the large number of frames per second, this type of lighting works well for that. And then our fourth pillar, which is very important to us also, is our consulting client education, like the event you're listening to today would be under this, as well as our standards activities. We attend several different committees and subcommittees within ASTM, ISO, AATCC, and a number of other industry organizations. And it's another part of our business that really helps to support everything that we are doing in these other three that you see here. All right, let's go ahead and get started with natural outdoor weathering. And the first, I guess, documented testing that we have been able to come up with was, as you see this picture right here, this is from a weathering exposure of paints from 1906. So even before Atlas started, that was conducted by the North Dakota Agricultural College. That's now North Dakota State University, primary coatings university. And this was on their experimental station. And you see these wood clapboards here that were actually faced on a vertical orientation with the racks oriented north-south for an east and west facing exposure. We've kind of changed that, as we'll see during the course of today's presentation. But it's because of that they used to put these racks or the actual samples on these fences like this. And so sometimes you still see or hear people talk about the exposure racks as being test fences. So this goes back well over 100 years of some of the earliest weathering testing. Of course, that testing was done in North Dakota, where, as you might imagine, is not necessarily going to be a place that's going to have a lot of ultraviolet. Obviously, it's going to be really cold. And you may recall from the factors of weathering presentation, or part one, that kind of concluded with a discussion on climate and where people do testing. And so there's, as you might imagine, there's a lot of different climates around the world. You know, many of us live in these more moderate climates that we see right here. But as far as benchmark testing goes, what we really want to do is look at areas that maximize the temperature, which we have here on our x-axis, and also maximize the total amount of radiant energy, which is a value here that we have here on our y-axis. And so, as you will note, the primary areas that we do a lot of testing are in these subtropical areas or desert areas where we have high temperatures as well as high amounts of UV radiation during the course of the year. And that leads us to our reference climate zones, or what we sometimes refer to as our benchmark climates, that are, as much as anything, for historical reasons, when they recognize that, you know, the fact that high UV content and high temperatures tend to accelerate, or at least it's sort of a worst case scenario as compared to, let's say, cooler climates, you know, moderate or temperate types of climates. So on the left-hand side here, we see South Florida. It's basically just the very southern tip of Florida, which again, historically has been used for weathering testing in this subtropical environment. We have these extremes that I discussed, such as the high UV radiation content through the year, very warm, and also very humid. Not just humid, but also provides a lot of wet time. In other words, condensation, the amount of time that samples physically have water on them is very high here in the South Florida environment, because during the evening, as things cool down, it's very humid. Condensation forms on samples nearly every night. Testing that is done in South Florida is considered to be inland. This is not a corrosion site. There are other special places where we do that type of testing. So this is not an area where there is any sort of corrosion influence, or let's say coastal influence from sea air or salt spray or anything like that. But the commercial locations are going to be in an area where there's going to be minimal amounts of pollution, so that we get that high UV content in a relatively clean environment. Arizona, as we see here, is another place where a lot of historical weathering testing has been done, especially on automotive interior materials. Because of the dry nature of the climate, the very high temperatures and high UV content, automotive interiors are often tested in Arizona. Back to South Florida, that's where you see so many coatings being tested because of that moisture content. Again, we have the extreme conditions, a lot of radiant energy, very hot, hotter than South Florida, at least in terms of its maximum temperature, but now the lack of moisture, very, very dry. So we have higher max temperatures compared to Florida. And again, in all of the commercial sites that you see, you're going to be in areas where there's going to be very little pollution. so you don't block any of that UV or have any sort of pollutive effects on the samples on exposure. Just to throw a picture of this is the Atlas facility near Homestead. We have actually two different locations that are just a little ways apart from one another. This picture would be kind of facing northwest, as all of the racks are facing the equators we see right here. We'll talk about some of these special projects that we have down here. And then we have a secondary site that you see right here. This is kind of facing northeast, if you will. And again, you see a lot of just racks and racks and racks of different kinds of samples. Again, we're talking now about the southern tip of Florida, just south of Miami. North of here is not considered a subtropical climate. It really is just this very southern tip of Florida. Here you see a picture of the DSET laboratory site near New River, Arizona, just north of Phoenix. This picture is looking kind of northwest. Here is a picture of where all of the racks are located. This area back here as well. And then here is where we have our natural accelerated test field that I will speak about in kind of the second half of this presentation. The climate here it's in the Sonoran Desert. We're high, a little bit above the altitude of Phoenix, so we get away from any sort of pollutive effects that we see right there. As mentioned, automotive interiors and building products are primarily what are tested here. I will talk about this natural accelerated testing here. This is also where much of our solar photovoltaic and solar thermal testing takes place, is in this area, in this particular facility. Now, we talk about those benchmark climates, but there are other climates as well, and there sometimes is a call for testing in some of those. And so at Atlas, we have what we call our Worldwide Exposure Network, or a WEN, and this shows just a number of the different climates and different locations where we do testing. There is a high altitude test site that is a little over a mile in altitude, about 6,000 feet near Prescott, Arizona. So high amounts of UV in this area, but also higher altitude. Alberta, Michigan for cold climate testing. We do have racks on the roof at our laboratory weathering sites. Here you see some other ones. We'll talk about some of these, some pictures about some of these for Jacksonville, Florida for automotive etch, corrosion testing sites, a Mediterranean benchmark site near Saint-Maurice-sur-Mer, France. This is just on the southern border of France, right near the Mediterranean. Hoek van Holland, which is a site recognized by the European Coil Coatings Association. And so this is just off the North Sea. And also a benchmark tropical climate in Chennai, India, as we note here. We also have some other entities that are not necessarily Atlas owned or run, but that we can also test in these other locations as well that you see listed here, including in the southern the southern hemisphere, tropical and temperate climates for testing here in Australia. So let's talk about the solar radiation is received during the course of the year at these locations. And because you'll notice that there is some differences. Now, some of that is due to cloud cover, but you'll also see differences as it relates to the angle that the samples are actually on exposure. Different exposure angles, you get different amounts of radiant energy. And this is due primarily to the path of the sun during the course of the year. So for example, at the equinoxes, let's say the middle of March, middle of September, at a northern exposure in the northern latitudes, if this is our horizontal surface, you'll see here that this is the angle that the sun would hit these samples at this horizontal surface. Whereas at latitude during the equinox, the sun's path at solar noon would be very nearly perpendicular, okay? You'll notice here in this red line, this would be a vertical exposure coming off of the Earth as we see right here. But as we go to different times during the year, okay, so such as the summer solstice, 21st of July, the horizontal surface will now be nearly perpendicular, and there's hardly any radiant energy other than what can be diffused by the atmosphere on a vertical plane. And then again, here's our at latitude angle. And then the opposite of that on the winter solstice, Again, the horizontal surface does not see a lot of radiant energy, especially as you turn further to the north. And this is where at 90 degrees or perpendicular, you'd see the most radiant energy when the sun would be lower in the sky. So it's always important to understand that sample orientation will have an effect on how much radiant energy that material might actually see during the course of the year. I'm not going to go through all of these numbers, but just point out a couple of things. Here you see some of the average radiant exposure amounts during the course of the year. From 2009 to 2013, it's for 90 degrees. And here you'll see that because we are relatively further south, here in the Phoenix and Miami area, that the amount of radiant energy in the UV part, especially in the UV at 90 degrees, is significantly less than when we tilt those samples at either a 45-degree angle, the latitude angle, or at 5 degrees. So here you see the values with a couple of different sensitivities of the radiometers that we have, and some of these other locations that you see right here. Now let's talk about direct weathering, the actual practical application of the weathering testing that we do. And it's a pretty good picture that really shows all of the, or most of the different angles of exposure that are common, such as 90 degrees. So when I refer to 90 degrees south, we are talking about that angle facing south from the horizontal. So 90 degrees to the horizontal would be a vertical exposure that you see with the racks that are here at the far end of the field right here. These racks that are located right here would be at 45-degree angle, and that is a very common angle for just about anything. You see many, many racks at 45 degrees. This helps to kind of minimize the variation that you get during the course of the year from winter to summer by having racks exposed at either this 45-degree angle or for what we call the at latitude angle. Here in Phoenix, Arizona, that would be at 34 degrees facing south. By the way, I know that this is Phoenix, Arizona, not just because of the mountains in the top, but you'll also notice that the ground cover here is gravel. And that is actually something that is referenced in the ASTM G7 standard. This is the standard, this as well as ISO 877 and ISO 2810, that really describe the practice for exposing materials to direct natural weathering, or sometimes what is referred to as a static weathering test. And they go into things like the minimum height off the ground, the actual ground cover, any potential effects of shadowing and that sort of thing are all covered within this practice itself. So here you see, by the way, a picture of our facility in Florida, because there the ground cover is typically going to be low-cut grass that you see right here. Obviously, it's for kind of practical reasons as well. In Phoenix, it's hard to get anything to grow, and in Florida, it's hard to keep anything from growing, so it is kind of practical to do it that way. The main punchline of this slide, however, happens to be the different types of backings that you see. And this is one of the important things when people send us materials for testing as well. How do you want that backed? In an unbacked configuration, such as what you see in this slide or this picture right here, or having your samples mounted directly to a substrate, typically a faced plywood or something like that, as you note in this slide right here. And that is an important thing to always recognize this, because you want to do whatever is nearest to what the end use application of that material will be if it was used in its normal service environment. And let's give you some examples of where that would be. So for example, here's a picture of some coated polycarbonate materials. It's very clear, you'll see some delamination that is going on here. Delamination is actually happening on both sides. The material is coated on both sides. And because this might be used, for example, for something like an awning material that you might see like this, an unbacked exposure would be the correct way in which to test that material, because this would be more similar to what that material might see in its final end use application. Here you see some backed exposures where the materials are exposed right up against this plywood right here. It's kind of protected, as you see here, and so you'll get very little cooling on the back side of the samples. And why this is so important, this unbacked versus backed, is really due to temperature. Backed exposures typically will always have a higher specimen temperature than unbacked exposures, because with unbacked exposures you get a little more cooling from any sort of airflow, wind that is blowing in and around the racks. And so this can be very important for looking at different types of degradation. Here's a good example of we had these long strips of vinyl material that we were supposed to expose, and to try to keep them, as close as possible to that south-facing 45-degree angle that we were supposed to do. We, to kind of help, kind of bring up the center part and support it, we put these materials on some 2x4s. And here you can see in the backed area, right behind these 2x4s, where you saw this kind of what I assume was probably some sort of thermal degradation occur as a result of the backing behind this 2x4. Whereas away from that, you see that because of the cooling effect, sample temperatures were a little bit lower. You didn't see that type of degradation. So some people may not think about this when they're doing those exposures, and this is a good slide to say, hey, be careful about this kind of thing. So what you see here is some corrugated material that was used primarily in things like greenhouse skylights, some of the clear materials that you see. And because when you have an exposure, you pay for either a panel, which is usually like a 3-inch or 6-inch by 12-inch panel, easily mounted in the racks, or a sample, which is where maybe there's some labor involved in actually exposing the material. And there's a little bit difference in the price of that. Well, we had one client who was unhappy that we were charging the sample price versus the panel price. And he said, well, hey, I'll just simply attach my materials to some plywood backing and save a little money, because those open backed exposures were a little less expensive. So that put his material now in a backed configuration, because now they were backed up against this plywood that you see right here. Well, because of the corrugated nature of these materials, you can see that in these touch points where it was actually backed, you got some pretty severe thermal degradation in these areas right here that likely would have never happened, because here in these unbacked locations, you don't see that same type of degradation. So based on this, it would be pretty clear that with this, the end use of this material, that this was mounted in a condition that did not match the service environment and really was probably considered to be an incorrect exposure. To quantify the temperature difference that we see in a backed versus unbacked exposure, I want to explain some things in this slide that you see right here. So we have our ambient temperature, which is noted by our little stars. It's always going to be a little lower than our mean monthly temperature for any material on exposure, because of it absorbing the actual sunlight. What I want to note, first of all, you'll see here that a backed black sample is always going to be much, much higher than anything else, absorbs a lot of solar radiation, and it's in this backed configuration. But what I think is kind of interesting here is note the dark blue diamonds and the kind of the turquoise colored X's that you see right here that pretty much almost mirror one another throughout the course of the year. Well, one of these is an unbacked black material, and the other is a backed white material. So we basically have turned this black sample, in terms of its temperature profile, we've turned this white material black, or just simply by backing it. So as you see, the temperatures are almost the same between a backed white material and an unbacked black material. Here's an example of a 5-degree exposure, which is another common exposure angle, especially in Florida, where you get a lot of diffuse radiation. And so this would be good for something like decking materials and let's say automotive materials, where you get in that end use condition something that is in more of this, a horizontal way right here. With these, the actual rack itself is oriented at 5 degrees, but for these materials, you'll note that we have these little teeth on them so that the actual decking boards are right at 0 degrees. So that any sort of water that might pool or pond on those decking boards, that would actually happen with the samples oriented at this angle of exposure that you see right here. So another way that 5-degree exposure comes into play is for automotive materials, and many automotive paints and coatings are exposed inside or on top of one of these black boxes. And this is referenced in ASTM D4141A. This is where we see these black boxes. And so we basically cover the top of the black box either with blank samples or actual client exposed samples that you see right here. So during the day, similar to an automobile, the black coating that we see right here will heat up the actual sample on exposure a little hotter than it might be if it were just simply in its unbacked configuration. And then at night, we kind of accentuate the amount of wet time because all of this black coating is going to emit all of its energy back out into the sky and helps to promote some condensation that we then see on these lighter colored samples on the top here. Again, this kind of simulates those characteristics of either the hood of a car, the trunk of a car, or let's say the roof of a car, where we get a lot of wet time as well as higher temperatures. And with this 5-degree exposure in Florida, high amounts of UV. The slides that I showed so far were all for direct weathering. In other words, nothing filtering the sunlight other than the atmosphere itself. But we also do underglass testing, or what we sometimes refer to as indirect weathering, following either AATCC or ASTM or other procedures that you see right here. So we can do this in a number of different ways. We can, in the same way, do backed or unbacked exposures. We can do backed or unbacked exposures with underglass as well. Sometimes we will put these materials inside a black box under glass. Sometimes we refer to that as a BBUG exposure, black box under glass. And so here's just some examples of that in these photos that you see right here. Now, with the typical cover glass that is used for these types of exposures is always going to be basically single strength, 3 millimeter thick glass, unless you tell us otherwise. And that can be very important, again, depending on the end use application. As you'll see here, this is a transmittance graph, a spectral transmittance in the UV part of the spectrum for different types of glass. And as you can see, whether you go to a laminated glass or a tinted laminated glass that might be used, let's say, as a windshield on a car, the cut-on wavelength of transmittance is going to be much different than it would be by just using either single strength window glass. Even the tempering process can affect the transmittance of the glass a little bit that you see right here. So if you are testing a material, you're producing a material that maybe is for an automotive interior application, especially something that might be, for in the instrument panel area or something like that, testing under laminated glass or other glass, usually supplied by the client themselves, can be accomplished. So always need to know what is that end use application and what type of glass should be used, because that can greatly affect the amount of UV exposure on that material. Now, there are some kind of fun things that we do testing on a lot, just a couple of slides on that. Things like golf balls. I lose my golf balls way faster than any sort of exposure would have any issues, so that's not a big deal. We did some safety testing on bicycle tires where the customer would then do impact testing to ensure that these tires won't, the rim of the tire, will not become too brittle. We do north-facing exposures where we look at mildicides or fungicide studies on these wood clapboards that you see right here. These are actually facing north to maximize that mildew potential. And then photodegradable plastics that are maybe not recyclable have been tested as well. We do testing on roofing decks. Here you see some of those 90 degrees south and north facing exposures, photovoltaics, and yes, these are actually swimming pools. We weren't actually testing the swimming pool itself, but we were actually testing the chemicals in the water. And so this test is now completed, but there was a time when one person every day would basically, his job was to go swimming. He'd go into these swimming pools, collect water. We do analyses on the water to see if the chemicals would be basically be depleted as a result of that UV exposure. Kind of a interesting, fun test. We're starting to see a lot more testing with food and beverages as well as packaging, as they're trying to go to either more clear packaging to show the bright colors of the new, let's say, sports drinks and that sort of thing. And also going to, lighter colored materials and also things that can be recycled and that sort of thing. Testing on packaging or the actual material itself can be done. Here's kind of an interesting example right here where we tested some sports drinks. You'll note on this just a standard 5-degree exposure right here. And after 10 days, the coloring in all but these red material drinks right here essentially went away, just 10 days of exposure. So now I don't know, most of the time people would consider that, you don't want to see any change, but I'm not so sure if I'd want to put this that lasted 10 days outside my body as compared to maybe some of these others. I'm not sure which would be the best. Here you see some testing on the actual packaging material where we masked a piece of this, and they were looking at the inks of these bags of chips and actual wine bottles that you see right here, some other different types of outdoor exposures. Now, you noted that I said before that the small, like the 6-inch by 12-inch, 4-inch by 12-inch panels are those panel exposures. Well, there's samples, and then there are samples. These are actual custom test houses. You can do these in both Arizona and Florida. And as you see right here, it's actually a window manufacturer that is testing these in their actual end-use environment. These are commonly facing more of a southwest location to start to get some of that sunlight as the sun's path starts to go down in the western part of the sky. And you'll see these where these are actual air-conditioned houses, and they will do lots of different types of looking at physical degradation types of defects of some bowing and that sort of thing, with the window units actually in their true correct end-use environment. Going from architectural to automotive, we do full car enclosures. Oftentimes these are associated with temperature testing. And so the screens that you see around here are, number one, to confidentiality reasons for, obviously any visitors that we have cannot get into these little car pens, but this also helps to keep the wind down to maximize the temperatures that we might see for a number of thermocouples that we might have located on the inside and various locations of the automobile. Kind of an interesting thing with automotive temperature testing is we can do what's called a sun tracking carousel exposure, where we will mount, over 100 thermocouples in just about any different surface and location and material inside a car that we see right here. And then we will orient the car so that the first day, the front of the car would be facing the sun, and it would track the azimuth of the sun during the day. The next day, we would face the backside of the car to the sun. The third day, the door, the driver's door, passenger door, and then maybe go at these 45-degree angles. So that over an 8-day cycle, we're going to basically get a direct exposure on just about every surface that possibly could be inside this automobile. So using the sun tracking carousel and basically monitoring temperature measurements, continuously during the course of the day. And in doing so, we can come up with maximum temperatures that we might see. And here you see some of those temperatures that can be used, not only just good information on what the max temperatures might be, but this kind of information also can be used in test method development when looking at different automotive interior testing. For example, you see here this what Atlas refers to as an IP-DP box, instrument panel door panel box. There are a number of different specifications that we see right here. These can either be facing the sun at a 45-degree angle, or tracking the sun, primarily just in Arizona, where the angle stays the same, but we track the azimuth of the sun during the course of the day. And from that data that I noted before, we can limit the temperature of a black panel that is located inside the box here to whatever might be the maximum temperature that particular material might see. Some examples of temperatures are things like 85 degrees C, all the way up to about 110 degrees C, to match that maximum temperature that we might see on an instrument panel itself. Different types of glass can be installed, and then once the temperature is reached during the course of a day, a small little fan recirculates some of the air from the bottom of the chamber or from the bottom of the enclosure up through the top. So it's not a temperature controlled box, but it is a temperature limiting box. Here you see just some different types of exposures between backed and unbacked and the different exposure angles. Again, as you might expect, things like exterior materials and corrosion tests and windscreens are going to be in an unbacked configuration, whereas roofing materials and PVC siding and things like that would be in a backed orientation. Now, often people ask, well, how long should I put something out in the sun? And of course, that all depends on what is the expected service life of that material. So for example, we might have real short durations. I noted the packaging material for things like soda and those sorts of things that might even be just a fraction of a day. Looking at implant sutures for cataract surgeries, things like that, half a day. And then some of these other things, where things like eyeglass lenses, this is kind of an interesting one. We would do an exposure for only around 2 weeks. And you might think, well, man, I hope the my glasses, that my prescription doesn't change that quickly. Well, what they found is that the actual amount of ultraviolet radiant exposure for a 45-degree angle facing south in Arizona during summer months in 2 weeks is roughly equivalent to the amount of exposure that the glasses would see in its end-use environment, because of course we don't always walk around 24/7 staring at the sun, right? So a 2-week exposure is long enough to give the client some comfort and reducing the risk on any sort of failure happening, such as adhesion loss or something like that, even after 2 years of actual end use. But of course, for some materials like house paint, highway signs, those sorts of things, these are long-term duration exposures. What Mother Nature gives us is what we get. Basically, you can get some acceleration simply from exposing that material in its benchmark climate, such as Florida or Arizona, and then tilting it at, if it's going to be in a 90-degree orientation like a highway sign or an architectural paint in its end-use application, tilting it to, let's say, a 45-degree angle will accelerate that process, but it's still not going to be enough. So we're going to have to do some sort of an acceleration. Because as we've said before, a natural exposure 1 year in Florida, in the real world, takes about 365 days in Miami. Okay, but we know that we need to accelerate this because of economic competitive concerns. People can't wait for 10 or 15 or 20 years because the product development cycle is obviously much shorter than that. So there's a couple of different ways we can do that. One is to maximize the amount of radiant exposure during the course of the day. I briefly mentioned these. I kind of got ahead of myself a little bit, but we can do some things by changing the angle or tracking the sun. The other way that we can do this is by intensifying that natural solar radiation. So here you see an example. As I mentioned, a 90-degree exposure is going to see less radiant energy than a 5-degree exposure, especially in Florida. And here you see that. Here's my 90-degree exposure that during the summer months sees very little other than what comes from the diffuse or scattered radiation from the sky, as compared to that 5-degree radiation that you see right here. So you're going to see a pretty significant increase in the amount of radiation by tilting that material from its 90-degree end use to maybe a 5-degree. We could also track the sun with a tracking device such as this, and this gives us just a little bit more. Many people don't feel like it's really completely worth it to do this, but you can see here that for total solar radiation here in the summer months, we can get about 60% more radiation than we would get if that material was at its latitude angle that you see here. The problem with this tracking is that because, as you probably learned in part 1, the UV is more easily scattered, if you just simply track the sun, the amount of increased radiant exposure really does not go up all that significantly. So the other way that we can do this is by intensifying that radiation with the use of some mirrors. The generic term for this is a Fresnel or a linear Fresnel solar concentrator. Atlas's trademark name is EMA or EMAQUA, and that is an acronym that stands for an equatorial mount with mirrors for acceleration. The aqua then is Latin for with water spray. These devices are covered under a couple of standards, ASTM G90, which I will reference in several of the slides coming up, or also ISO 877-3. And the way in which these work, probably best to show this kind of in this graphical format that you see here. The direct radiation coming from the sun, sometimes referred to as the direct beam radiation, reflects off of these flat mirrors that are focused onto a single target board with the samples then facing actually away from the sun. So it's just seeing this reflected radiation from these different mirrors that we see right here. The instruments then will track the sun, both the azimuth and the altitude, during the course of the day, keeping the samples and that target board in focus. Here you see that full device where we can actually spray water on the samples as well. All of the primary functions and the requirements, the minimum requirements for this are covered in this ISO and ASTM standard. And that ensures things such as the mirror reflectance, how we measure the UV irradiance, how we measure the mirror reflectance as well, how we track the device and track the sun. Also, if there's water, the water quality in case any sort of sprays are used. And then the type and direction of the airflow, since we are exposing these samples to multiple suns, we have to do some things to try to keep them cool. If we look at the amount of intensification that we get over the course of the year, this slide, this build slide kind of does that for us here. Here we see the average Miami sunlight at latitude angle that you see down here. Well, measuring that in the target board of the Amakwa type of device, we see, as you can see, this increased amount of radiant energy. If we were to just multiply, look at what that multiplication factor is, looks something like this. And then if we were to kind of just linearize this a little bit, what we get is about a 5 to 6 times acceleration, or 5 to 6 times more radiant energy over the course of the year as compared to just a static at latitude angle either in Florida or Arizona. And here you see that comparison of the amount of radiant energy we get in total solar and UV as compared to these different angles of exposure that you see right here versus Amakwa. Here's some of that data and that intensification that you see. Okay. Now, you might ask, well, how do we time these exposures? Oftentimes, it is done by, let's say, what we call, and I'm using air quotes here, an equivalent year of radiant energy in either Florida or Arizona. But of course, in the wintertime, we see much less, radiant energy than we do in the summertime. It's just natural seasonal variation. So there are ways in which we can track that and estimate the amount of radiant exposure to reach a specific amount of typically megajoules per square meter of total UV. On our website, under the Knowledge Center and Data and Tools, you can find this Amakwa radiation duration estimator, where you can put in your start date, what type of exposure you have, put in the amount of radiant energy, and it'll tell you approximately how many days it would be for that to complete. As you see there. Now, with this device, we can have different spray phases. Cycle 1, as is referenced in ASTM G90, is a daily, hourly spray during the operation, where for 8 minutes out of every hour, we spray the samples with DI water. This provides sort of a thermal shock, if you will, on the samples. Cycle 2, which is an Arizona simulation, since we don't see a lot of rain there, is no spray at all. And then cycle 3, which is primarily for coatings, to simulate that dew formation that you see every night in Florida, we spray the samples for 3 minutes and then off for 12 minutes, and that keeps the samples continuously wet during the course of the nighttime hours. And so that is the sprays that are done in the spray cycles that are referenced in these ASTM G90 standards. As I mentioned, we cool the materials that are on exposure with airflow in the front and back. We almost always use an unbacked exposure for this. You have to be a little bit careful because the samples need to be flat for this type of exposure. The maximum height of the sample is 6 inches because that is the height of the or the width of the target board. And also, you have to be careful about samples that are too thick or really, really heavy because the thermal environment is going to be dependent on that thickness of the sample, how much air it requires to pull away some of that heat, the thermal conductivity, and of course the solar absorbance of the sample itself. Now there are additional enhancements that we can do. We can control temperature with a variable speed fan. We can actually control the temperature to a replicate sample, take temperature measurements of a sample on exposure, let's say in Arizona, and then basically match that on this type of a device. We can actually also put the samples on tops of mat heaters to control nighttime temperature as well. If the intensification is too high, we can cover sets of mirrors and also have programmable spray cycles beyond those 3 that I referenced earlier. Now, one of the more recent developments with this type of exposure is with some different types of mirrors, some that we call cool mirrors that I'll explain here in just a little bit. The standard Emakwa mirror has very good reflectance all the way down to that cut-on wavelength of natural sunlight, so that you basically also see the right shape of the spectrum using those mirrors. But that also means that you see all of that visible radiation as well as all of that infrared radiation that sometimes can make temperature a little bit of an issue. So with the use of these cool mirrors, we can decrease the amount of IR radiation to better control sample temperature and still give us that same UV exposure and UV acceleration as with the traditional Emakwa. And the way that this ASTM standard, G90 standard is written now, these still comply with that, with the wording in that standard. To kind of show the way these mirrors work, here, for example, pretend that we have our mirrors here on this parabolic tray that we see here. Okay, all of that light coming from the sun hits our mirror in this, right here. All of the near infrared or and some of the longer wavelength visible actually transmits through the mirror, so that only the UV and some of the shorter wavelength visible are reflected onto our sample plane that we see right here. And to show you of what this looks like as far as the spectral reflectance, you'll see this graphic right here. So what's really being reflected is all of the radiant energy from the solar cut-on here at this 295 nanometer point up to about 450 to 500 nanometers. Almost everything else is transmitted through, and this is what allows for those cooler temperatures to be had on this low temperature Emakwa type of device. This shows you an example of what those temperatures look like. Here is a standard G90 exposure of with a black standard. So this would be an insulated or a backed black panel exposed on a traditional Emakwa type of exposure. And here's the temperatures for the low temperature EMA, as well as a black standard exposed just in a horizontal exposure out in the static weathering field. And as you can see, the temperatures are very consistent. This is over the course of 2 days. We did not hold the temperatures very well with the traditional Emakwa exposures. But we do get that higher amount of radiant energy. Here you see with the low temp Emakwa, the radiant energy during the course of 2 days versus traditional Emakwa, where the reflectance is in the UV is actually higher with our cool mirrors, as compared to the radiant energy that we get on a traditional static horizontal exposure rack. Remember, I said that it was roughly 5.5 to 6 times. Well, you'll note that our peak here is about 0.5, and you go about 5.5 to 6 times over that, and those are the numbers that we are seeing right here. Now, one of the newer things that we've done is to actually take those cool mirrors now, and rather than using 10 mirrors onto this longer target board, we can actually cant these mirrors a little bit, angle them in, have a shorter target board, but now have a total of 20 of these cool mirrors, all reflecting onto this target board that we see right here. Here you see a nice picture of what that cool mirror looks like. It's reflecting all of the UV and shorter wavelengths, and you can see actually right through the mirror, which is that longer wavelength visible and into the out into the infrared. So by doing this, we have better control of sample temperatures because we're decreasing that IR irradiance, but now we can get an intensification of up around 10 or 12 as opposed to 5.5 or so with a traditional EMA or Emakwa. We can also use the same standard sprays, cycle 1, cycle 2, cycle 3, which we would then call either an ultra accelerated EMA or ultra accelerated Emakwa type of exposure. We now are kind of using that term UA EMA or UA Emakwa. You see the black panel temperatures. The red and blue lines here are traditional EMA exposures. And here you see the UA backed and unbacked, where our temperatures are decreased by about 15 to 18 degrees as compared to its counterpart EMA exposure. We've done some testing with polystyrene chips, looking at yellowing, both with the UA EMA and the traditional EMA. Here is the number of days of exposure and the amount of yellowing, and looking at the delta B value of these clear polystyrene chips. And we saw that reciprocity held relatively well when we regraphed this data based on the amount of radiant exposure during the test, as you see right here. Pretty good R-squared values. So it's kind of an overview of this. We have our traditional EMA or AMOCBA. We use these 10 mirrors. We can then use the cool mirrors in that same configuration to bring the temperatures down quite a bit. We can then go further to use this UA AMOCBA, where we use 20 of these cool mirrors. And the latest technology that we have now, realizing that sometimes the temperatures aren't quite high enough using all cool mirrors, is now this hybrid approach, where we use a total of 20 mirrors, but some of them are going to be the traditional mirrors that will reflect back all of the visible and infrared radiant energy, and then some of the traditional cool mirrors that are only reflecting the UV and visible parts of the spectrum. And so in doing these, we can actually control the temperature even just a little bit better with this hybrid approach. Now, the final natural ultra accelerated way we can do things is with what we call the UAWS exposures. And this was something that was developed in conjunction with NREL and a Russian institute, as well as Kelly Hardcastle with Atlas, that uses a number of these cool mirror facets to actually have a real parabola of mirrors onto a very small target board that you see right here. You can see how brightly lit this is. Again, very little IR radiation. But in doing this, we can get up to 63 times an intensification on that target area of UV irradiance. And these types of devices and this type of an exposure has been good for something that has an extremely long service life, things like transparent glazing materials. The samples actually sit on a water-cooled panel that we see right here to help keep the temperatures in check. Sometimes we'll do testing for photovoltaic applications as well, and basically anything that performs well with the high intensification from either the traditional EMA or UA EMA type of exposures are potentially can be used for this. We have, I think, either 3 or 4 of these units that are now functioning at our DSET location. Let's talk, just going to shift gears just a little bit to kind of conclude things. That is how we measure these factors of weather for weathering tests. And here you see a picture of our racks, our radiometer rack and black panel temperature rack. What you're seeing here is different angles. So at latitude 45 degree and 45 degree under glass. In green here, these are our total ultraviolet radiometers measuring radiation just in the UV part of the spectrum. These other things that have these little white discs around them are called pyranometers that are measuring total solar, also at those same angles. And then we will also measure black panel temperatures, white panel temperatures, as well as the traditional weathering factors such as ambient air temperature, relative humidity. We also measure wind speed, wind direction, rainfall, and those sorts of things too, in this little enclosure that you see right here. All of this data is collected on a minute-by-minute basis. For a fee, we can provide customer reports, usually on about a 10-minute average. This kind of inundates people with almost too much information, to be honest with you. So now more like a 10-minute average is what's more common for some of these customized reports. And then we have daily data and our weather summaries that are also reported that are free of charge. We also do radiometer calibrations in case you have your own, own weathering field and have some radiometers out. See some of these radiometers on exposure that we see right here. These are calibrated. These calibrations are traceable to the World Radiometric Reference. We're actually in the process of having our materials and our sensors sent to Davos, Switzerland, where this is done. It's also traceable to NIST. Our spectroradiometers are traceable to NIST. And they do comply with ISO 17025 and are a part of our overall laboratory accreditation. Now, there's another customized webinar that we do a full hour on evaluations. We don't really have time to get into those things as well. In my experience, we probably about 50% of the samples that are on exposure, we do some sort of an evaluation, color measurements, gloss measurements, visual assessments, those sorts of things, digital photography, so on and so forth. So be looking for those, an event that is on evaluation techniques that are done in conjunction with many of the natural weathering exposures that we do. So in conclusion, we know that weather and solar radiation are variable. They're seasonal, daily, even yearly variations. There's a lot of different things to take into consideration. The angle of exposure, open-backed versus backed, that can be rather complex. We monitor the exposure environments. We don't really worry too much about secondary factors here. It's just really the primary things, that light, moisture, temperature. These things can be quite time consuming, generally non-repeatable, non-reproducible, but we can do some acceleration with tracking and intensification techniques. Okay, this really concludes things. The third part is on laboratory weathering. I want to try to get to some questions here before we finish up. So I'll be looking for that in an upcoming event, and then these last three that we have right here. You can get to these through our different resources. We've got a blog going now. You can find recorded seminars at our on our website as well. We do have a LinkedIn presence, and future seminars, look for our calendar for those sorts of things. Let's take a look and see what questions that we might have. And let me see if I can pull this up here. Questions. Okay. I thought I had a question. Maybe that was in the chat. Okay, yeah, it doesn't actually look like. I'm sorry. I thought there was a question, but guess we cover everything relatively well. We are just nearly at the top of the hour again, and so anyway, so please take a look on our website, find another event. Really hope that you will be able to participate, and that will conclude our event for today. Again, if you do have any questions, when you get the presentation, you take a look at it, you're kind of digesting things through, please feel free at any point to send me an email at matt.mcgreer@amatech.com. You can also go to our website. You can type in inquiries there as well. I hope you enjoyed our seminar for today and learned something useful for your work about the natural weathering testing. Thank you very much for your attention, and you all have a good day. This concludes our webinar. Goodbye.